In this lecture, we're going to look at eigenvalues and eigenvectors. Suppose natural bases. In other words, we want 0, 1, 1, 0. And a linear transformation that's given by that matrix with row 0, 3, 0, and then 0, 2. We multiply that matrix by a vector, x, y, and we then get this result here. Okay? What that does, it stretches the E1, and recall that E1 is given by, and E2 is the other basis, is 0, 1. All right, those are your elementary vectors. So what that does, what this vector there does, is it stretches the E1 and E2 vectors as we show below here. All right, notice that this here is our normal basis, so we have a vector E1 and the vector E2, and these directions are in the negative direction, which means it's simply multiplying by a -1. So the circle of unit radius, this circle here, all right, becomes an ellipse once we do the transformation given by this here. Okay, and you can see right here that if you look at this 2y, here's the 2y there. So if we look at that, you've gone from a circle of unit radius to, so a circle of unit radius to an ellipse, and it's poorly drawn, I must admit, which has this property that it's stretched by a factor of 3 in the x direction and 2 in the y direction. What kind of transformation is this? Well, we denote a transformation by txy, and this here becomes the transformation, 3 times x and 2 times y. Suppose that we have the following transformation relative to the natural basis. So here we have a much more complicated transformation, all right, because it's given by an equation multiplied by 1/5, and the second component is a combination of that x and y, just like the first component. The matrix for t is given by 12 over 5, minus 1/5, here's your -1, there's your 5, and the same thing here, this 6 minus 6 over 5, and 13 over 5 given by those two. Now, this is relative to the natural bases. Suppose we want to change the bases from 1, 0 to 1, 2, and from 0, 1 to -1, 3. All right, the matrix for this is given by what we had previously. Okay, our previous result here, given this diagram there. So now what we're doing is we're expanding in this direction here. There's your 1, 2, and here's your -1, 3, all right, which corresponds to that. But notice that these are not orthogonal. Here's your orthogonal given by that little square here. And what we're doing now is we're stretching along this particular direction. All right, so we do a transformation of the xy coordinate system here to x prime, y prime, where x prime is still orthogonal to y prime. And before the transformation, in the normal bases, we have our unit circle here. And after the transformation, we've not only stretched it along the x and y axes, all right, but we've actually first transformed from the x to the x prime basis. All right, we've rotated it and kept it orthogonal. Now consider a transformation in 3 space. Okay, so this is a transformation in 3 space. that we define by this transformation on the first row, if you like, this on the second, and 0 on the third, and we define this on the bases. Notice this basis, this is your E1, but this is not your E1 anymore. This is a direction 1, 1, 0, and finally a direction 1, 1, 1. All right, we can represent that transformation by a diagonal matrix, the original transformation, given by this diagonal matrix. And what that does is it magnifies the vectors along the E1. It reverses vectors along 1, 1, 0, and it collapses to 0 vectors along 1, 1, 1. All right, so let's return to this transformation again, okay, which we have here and which we had above. For the bases, 1, 2, and minus 1, 3, and the matrix T, 2, 0, 0, 3. Then using this vector 1, 2, and this vector minus 1, 3, so those are our two rows, if you like, we get transformation 2 times in the x1 direction and 3 times in the x2 direction. All right, that gives us an idea of how we transform things along from one coordinate system to a changed coordinate system, if you like. Now, we define eigenvectors and eigenvalues. Suppose we have a transformation that's linear in n space. All right, so this is the transformation in n space. Now, if r is a scalar and x is a non-zero vector with some property tx is equal to lambda x, then lambda we refer to as an eigenvalue of the transformation t, and x, the vector x, is referred to as an eigenvector of transformation t corresponding to this lambda. So let's do an example in 2 space, all right, where we choose this particular matrix, all right, and it looks complicated, but we use it because things fall out pretty nicely in that particular case. All right, so we do a transformation, lambda x, and we have our original A matrix, which is given above here. This is our A matrix here. And we're going to multiply it by a vector along the x and y directions. And that's equal to lambda xy. So in other words, this is what we are looking to do. So when we bring this part to the other side of the equation, we get A, which is a square matrix. We get a vector of vector x1, x2, or xy of dimension p. And the same thing here is this vector here, and we subtract lambda times that vector. Now when we take this x out, we end up with this identity matrix, and we're subtracting A minus lambda times the identity matrix, which is the same as multiplying each element of this vector x by lambda, and that's equal to 0. All right, now when we have this result here, all right, what we do know is that x is not equal to 0. All right, why do we know that? Well, we know that to solve this equation, these two values have to be or at least one of them has to be non-zero. So if that's the case, all right, we can take this out and this becomes 0. But since vector x is not equal to 0, then the determinant of A minus lambda times the identity matrix must be equal to 0. So we denote this determinant by these straight lines here. So A minus lambda times the identity matrix has to be 0, and we refer to this equation as the characteristic equation of matrix A. So if we find the determinant of A minus lambda I, we know that it's a polynomial of exact degree p in variable lambda. And we can show that for our two-dimensional case as follows. We subtract, so if we go back to the original matrix here, this A matrix, but we've subtracted the lambda out in these two cases, or these two elements rather, this element and that element. Remember, on the identity matrix, you've got a 1 and a 1, and these are zeros. And when you subtract the identity matrix multiplied by that scalar lambda, the unknown scalar, then you get this structure here. And when you're looking at the determinant, you're taking the determinant of this here. So we take this element, A11, multiply it by element 2, 2, and subtract from it this number multiplied by this number, which in the case we got a minus here becomes positive. So we'd have 9 times 12, which is 108 over 11, okay, which gives us this result. And the first part is this minus 14 over 11 minus lambda times 25 over 11 minus lambda. And when we factor that all out, we get lambda squared minus lambda minus 2 is equal to f of x, which we set equal to 0. Solve for lambda, and we've got a quadratic equation, so we know that we probably have two solutions to it, and that's indeed the case, because lambda minus 2 times lambda plus 1 is equal to lambda squared minus lambda minus 2. And this implies that we have two eigenvalues, lambda equal 2 and lambda equals minus 1. So now we've got to solve for our eigenvectors, and we do that by first setting lambda equal to 2, which means we get minus 14 over 11 minus 2, 9 over 11, that one didn't change, minus 12 over 11, and 25 over 11 minus 2, multiplied by the vector x, and set equal to the vector 0. That gives us two equations, minus 36 over 11x plus 9 over 11y equals 0. So that we get by multiplying this by this and then adding this times that. All right, and we do the same thing here. We multiply minus 12 over 11 by x, 25 over 11 minus 2 multiplied by y, and then that gives us this equation here. Solving for x and y gives x vector equal to 1, 4. Doing the same with our second eigenvalue, lambda minus 1, we get this result here, and when we multiply this matrix by this vector, we get two equations. This one here, minus 3 over 11x plus 9 over 11y equal to 0, and minus 12 over 11x plus 36 over 11y equal to 0. Solving these two, we get a vector 3, 1. So we have two solutions, or pardon me, we have an eigenvector 3, 1. Now, of course, and one of the things you're going to do in the labs is that you can find these using just a function within R itself, within the software package R, and you'll learn how to do that in the lab. All right, what does this imply? Okay, if we go back here, we got these two solutions, 1, 4, and 3, 1. So vectors are stretched by a factor of 2 along the line determined by vector 1, 4. All right, so vector 1, 4, and the associated lambda or eigenvalue 2. And vectors are reversed along the line determined by vector 3, 1, because the other eigenvalue was minus 1 here. So we reverse the vector along the line determined by the vector 3, 1. So what does this look like when we graph it? And it's not a pretty graph, partly because I'm not a very good drawer. And I must admit this package that I'm using will allow me to write a straight line, all right, or draw a straight line. So what we have is we have this black line here. This is our original basis, all right, your original two-dimensional coordinate system. And what we're doing here is we're pivoting it around. So we're pivoting around to the blue line, all right. And we also have these vectors, the 1, 4 vector, and this isn't drawn very well either. And we multiplied that by 2, so stretch along the line should be, this probably should not look like that, but in any event. And we have this 3, 1 vector, which we multiplied by -1. And when we do that, we end up with a ellipse that looks like this. All right, it's probably a little fatter here than I have drawn it. And that's the result we get. So what we've done here, we've pivoted the original coordinate system, and then we've stretched this original unit circle, to become an ellipse. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.